Everyone, good morning to one and all. Everyone, good morning to one and all. Am I audible? Okay. I am myself Bharatvi Nair. I am standing here to present my MSc final year project about deep learning and chaos, a combined approach to image encryption and decryption, under the supervision of Dr. Shishichandra Muni. So the presentation involves the methodology of the image encryption and decryption with the help of the hyperchaotic 3D hyperchaotic maps and with the hyperchaotic map like 3D hyperchaotic maps and 2D membrane map. And it also involves how it is robust and reliable from on comparing other techniques. The proposed method is important for the following reason. So nowadays, so many data and images are being cyber attacked and are being stolen or misused. So image data and security and privacy for conserving it, it would be so many. This method will be so many up to an extent it will be robust and is for secure communication, for protection against cyber threats. These are all the main aspects of the proposed method. And its application, it is applicable in many fields, including military defense, medical fields, financial sector, streaming services, surveillance system, etc. So the chaotic maps that are represented here, the maps which show unpredictable behavior when it is subjected into initial conditions. They are the chaotic maps. Because of this unpredictable behavior, they are used. They can be used for the proposed method, that is image encryption and decryption. The two maps which are used here will be 3D hyperchaotic map and 2D membrane map. While saying about the 3D while saying about the 3D hyperchaotic map, when all three Lyapunov exponents are positive in a three-dimensional space, then the such map shows hyperchaotic behavior, and it is a 3D hyperchaotic map. 3D hyperchaotic map. The equation is as follows. Where x, y, and z are the three variables over discrete time steps, and a1, a2, a3, b1, b2, etc. are the parameters of the system. These are the figures obtained by varying the a1, a2, a3, etc. of the etc. parameters of the 3D hyperchaotic map. First one is as you can see, the first map is very much concentrated at the border points of the map, and it is not well distributed. The second one, an equally distribution, an optimal distribution of the points can be seen. And in the third one, the points are distributed, but the map is a little bit, the cube is slightly detangled in a slopewise manner. So, and in the proposed method, we used the second map as the optimal map. Now it is for 2D membrane map. It is a map. It is a map which shows hyperchaotic behavior when the two Lyapunov exponents show positive, and its definition it is defined as follows, where xn and qn are the state variables and k represent the parameters. This figure represents the three type of maps obtained by varying the k parameter, the parameter k. First one is obtained by setting k equal to 1.74. Second is k equal to 1.75, and third is k equal to 1.76. Among these, k k equal to 1.75 obtained map is considered as the optimal map for the proposed methodology. This is the neural network architecture. So how the image encryption and decryption is performed. First, we need to incorporate an original image into the as an input into the neural network. And after the original image is inputted, the input layer accept it, and so many processes and so many criteria are happens in the hidden layers, and as an output we get an encrypted image and a decrypted image as a result. At the same way, we can also reverse the process for decryption. We can put the decrypted image and the encrypted image as the input, and the process is reversed. This is the main outline of the deep learning of the neural architecture. This is the flowchart which represents how the decryption and encryption process is happening. So first of all, it defines the initial conditions for the parameters to work, and they generate a chaotic sequence which are incorporated into the pixels after the image is being loaded. After that, the image is resized to get to the optimal size of the original image, and after resizing, the image is the iteration has been initialized, and the decrypted image is after the iteration is happened, the image is encrypted. After encryption, the prepared data is formalized for CNN to incorporate into the pixel value. Now, the CNN is reshaped data for the to build the CNN model. The after the CNN model is built, we compile the model using Adam Optimizer and MSC, and we train that CNN model. Also, the model is trained to obtain the decrypted image. These are the result of obtaining the encrypted and decrypted image. We performed the analysis on 4 images, that is aeroplane, Rainier, brain, and Lena image. The first row is the original image. First column is the original image. Second is the encrypted image, and the third is the decrypted image of the corresponding images. Now it is the key aspect of key generation. It is for securing the privacy. Key generation is very important. So the more complex the key is, more secure the decryption process. Only after a person holding a right key can decrypt the image when he gets an encrypted image. This protect the image's privacy and prevent unauthorized parties to take part in it. This is the process of encryption that is mentioned as the flowchart. First, we start with the grayscale or colored image and set it to standard size of 512 into 512 pixels. Now, the chaotic sequences are generated using 3D hyperchaotic map or 2D memristor map, and after setting initial parameters. For each pixel, they performed an XOR operation, and the chaotic sequence are generated. As a result, we got a scrambled image in which the pixels are disoriented and rearranged in a messy manner. This is the process of decryption. Sir, can I move that box? So it is the reverse of the encryption process. First of all, the modular arithmetic regains the decrypted pixels in a bitwise XOR operation. CNN analyzes it and reconstructed the encrypted image. The order of the arranging the encrypted image is just the opposite of it being processed in the encryption format. And after rearranging all the encrypted images in a specific order proceeded by the iteration, we get a decrypted images. And for Adam optimizer and mean squared are the softwares and are the methods that help us to minimize the errors. Now for the after the image encryption and decryption, we need to check how secure is our methodology is. That is why the section security analysis is being taken. First of all, entropy analysis. It is a measure of randomness or uncertainty in the image data. So it is a pixel level examination actually. So, the pixel is arranged in a NumPy array manner, and each and calculating the probability of occurrence of each pixel in that array. If the value of the entropy is closer to 8 and not below 7, it up to the range of 7 to 8, then it is a very good encryption. After the encryption is being performed, I have formulated a table of entropy of original, encrypted, and decrypted images. For the aeroplane, the 6.578 is the original. For the encrypted, 7.97 is for the encrypted, and the decrypted 6.57 what we get. So here the focuses on encrypted image all are lying in the value of 7 to 8, which supports our methodology that it is reliable. Next one is correlation analysis. This is the statistical measure that says how the random pixels are very linearly related. The values close to 1 reflect very good encryption and decryption, and values near 0 suggest that image is very much complex and it is hard to recover. While also there is a negative coefficient which shows that the image integrity is very successful image integrity is very high and successful encryption. This is the correlation coefficient for colored images. So in the encrypted column, you can see that all the values are negative, so which indicates highly encrypted, and all the decrypted and original images are close to 1, which means the original image and encrypted images are very much closely resemblance, and there is no negative correlation between them. Now it is for now the next test is the anomaly detection. So it is the pattern identification mechanism. It means that how much the pixels are the pixels are closely similar to each other, how much they are the intensity, the shape, and the detection are as compared to the encrypted images. For that, we calculated MSE and SSIM. These are the two metrics. For mean squared error, MSE is low, indicating that there is very less error between the encrypted the original and decrypted images, which means the decryption is highly acceptable. And for SSIM, they indicate very high similarity, meaning that low differences, meaning that high differences, meaning that the encrypted images is very much different from that of the original image. This is the MSE value. Very low MSE value indicates high encryption. The SSIM close to 1 indicates the high resemblance of the original and decrypted image. Now for the histogram analysis, this analysis is conducted to find in what manner the pixels are being distributed. So this is the picture for the original, the encrypted and the decrypted images. For the encrypted image, all the pixels are distributed in a symmetric manner, but in the original and the decrypted images, they are not in a symmetrical manner. It varies according to the intensity of the colors and the pixel distribution. Now for the robustness to noise analysis. In This test is conducted using by injecting Gaussian noise. It is very much effective to know how much resistant our technique is towards the noise. For that, we took the variance of 10, 100, and 1000. For despite higher noise levels, our decryption and encryption algorithm hold positions for what they acquire. Still they are getting, means how they encrypt, how they decrypt, and for all this problem, they are not facing any more issues while injecting the noise. This is the images for first column is for 10, and second is for 100 variants, and the third is for 1000 variants. As you can see how much the intensity of the noise is being injected, and we can still understand what the original image is. Even if the even if I increase the for it up to 10,000, it will recover almost a very important parts of the information from the original image. Next is for the differential attack analysis. So differential attack analysis is mainly used for decryption algorithm for detecting patterns or vulnerabilities. So we test it using UACI and NPCR matrices. So there the results show NPCR and the result I have obtained show very low NPCR value and moderate UACI value. These are the percentage calculations. NPCR and UACI are percentage calculation. The UACI mostly preferably it should be 33% above. It shows very good decryption. For NPCR values, it should be up to 90 to 80 comparison. And this is the result I got, 99.9 for the aeroplane, 99.88 Lena and the Rainier, so on. And USAA values are corresponding 68, 47, etc. So these show that the proposed methodology is resistant to differential attack analysis. Now for the key sensitivity analysis. Previously I told about the how key is very important for this. So how a key can tolerate a minimal change in the application leads to a very bad decryption. So this figure is the evidence for that. Firstly I encrypted the image using the original key. Then I put a small change in the key, and I couldn't even modify the original image very effectively. I couldn't even decrypt the original image effectively. So here the modified key means the key that is altered with a slight change. So this method indicates that a perfect key can only decrypt the images using our methodology. No, a single change in the key can alter the the decryption as easy. These are the result I have obtained. We used the 3D and 2D maps and with the CNN for encryption to produce complex and encrypted images, ensuring accurate decryption. And we use a script, implemented a cryptographically secure random number generator to enhance key, which are with a high complexity, ensuring secure encryption. And the entropy value is approximately 7.598, enhancing high randomness and complexity. And we also showed the strong negative coefficient plain text, confirming effective encryption positive coefficient between the plain text and ciphertext. It is saying about the correlation analysis. It is being mentioned in separate manner. That's it. And the for low MSE value and high SSIM value supports how decryption preserve the image quality very better. And for the after adding a Gaussian noise, we hope to know that the decryption algorithm is very much resistant to Gaussian noise, and some important features can also be resolved if more and more noises are being installed, injected. So for the last topic, the conclusion. Our proposed image encryption method combines a 3D and hyperchaotic map and a 2D memberstate map, which is strengthened by a deep learning neural network. The idea behind by using 3D hyperchaotic and 2D memberstate map is because of its complex nature. So because mainly encrypted and decryption algorithm follows a minimum three-step process for encryption. But here there is only one-step process are necessary because of the complexity of the maps used here. And we ought to find the high entropy, correlation coefficient, and the resilience against Gaussian noise and differential attacks, all by demonstrating with each table and all, which supports our answer and which provide us a good intuition that it can be implemented for the future studies. And the future scopes include the video encryption and exploring of the quantum computation techniques for the enhancement of this in real-time applications. Thank you.